Good afternoon, everyone, and welcome to the WST Time Domain Working Group Seminar Series. Today, I'm pleased to introduce Sofia Bisero, a third-year PhD student at the Observatory of Paris. Her project, titled Gamma-ray bursts as multi-messenger probes, focuses on the detection and the study of electromagnetic counterparts of gravitational wave events, with particular attention to gamma-ray bursts and kilonovae. Sofia is actively involved in SWAM and in GRAVE collaborations, and within WST, she coordinates the multi-messenger subgroup of the time domain working group. She will discuss with us the synergy between WST and the Einstein Telescope in the context of the next generation of gravitational wave multi-messenger observations. Please join me in welcoming Sofia. Thank you for accepting our invitation. The floor is yours.
Thanks a lot, Julia. I would like to start from a reminder of the milestone event that gave birth to gravitational wave multi-messenger astrophysics. On the 17th of August 2017, for the first time, gravitational wave and light were detected from a binary neutron star system merger. You have here the gravitational wave signal and the short GRB detection 1.7 seconds later, detected by Fermi integral satellites. This sparked a multi-wavelength follow-up campaign that was unprecedented. And about 11 hours after this first detection, also the optical counterpart, the kilonova, was detected. And kilonova is the a thermal transient that is powered by the radioactive decay of our process elements. And with these events, an unprecedented data set of kilonova and gamma-ray bursts were collected. I report here a couple of very interesting examples. On the left, you have the time series of medium resolution X-shooter spectra of ET 2017 GFO. That were very important to study the physics of the phenomenon, to study heavy elements nucleosynthesis, and also to identify that transient as a kilonova. And it's the first time series of a kilonova like this. On the right, you have the multi-wavelength light curve of the short GRB afterglow. And this was the first monitoring of an afterglow seen off-axis that allowed the study of the structure of the jet, showing that indeed that jet was structured. In general, why is it important to research electromagnetic counterparts of gravitational wave events? It has an impact in many fields, for instance, in cosmology, allowing to give independent measurements of the Hubble constant. Also, gravitational wave triggers are a unique opportunity to see off-axis afterglows and study the structure of relativistic jets. It allows to understand and study the population of binary neutron star system merger in all its variety and massive star evolution, as well as studying the kilonova population in all its variety and the contribution of kilonovae to heavy elements nucleosynthesis. Up to now, we had only one joint detection of gravitational wave and light from the same astrophysical source, and the current rate with the gravitational wave detectors are still low, but this will change completely in the future with the next generation gravitational wave interferometers like the Einstein Telescope. ET will be sensitive to low frequencies, allowing to access the DNS signal before merger, and also it will allow to access the post-merger phase. It is in the S-phase roadmap to be realized in the 2030-40s. Now, what are the challenges in detecting, identifying, and characterizing the huge number of DNS that will be detected by ET? Well, first of all, the gravitational wave signals will have pretty large error regions. In this plot, you see the redshift distribution of DNS detected by ET. This is from a paper by Leonora Loffredo. And different colors correspond to different characterization error regions. And you see that as we go farther in distance, as we access a larger volume of the universe, then we have also less precise localization regions. On the electromagnetic counterpart side, the sources will be faint. You see here the magnitude as a function of redshift of simulated kilonovae, with these black points, black symbols referring to recently detected kilonovae. So you see that with respect to the simulated population, we really accessed only the tip of the iceberg, and that we need high sensitivity facilities and also facilities with large field of views. Spectroscopy will likely become the bottleneck of gravitational wave multi-messenger science. It is the only robust tool that we have to identify the nature of transients. This was important in the case of ET 2017 GFO. And in the context of next generation gravitational wave interferometers, there will be a lot of counterpart candidates detected within the error region of gravitational wave signals. And also within the error volume of such signals, there will be a lot of galaxies. So galaxy targeted searches with current electromagnetic facilities will be unfeasible. In this context, integral field and multi-object spectroscopy can really play a key role in this game of identifying and characterizing electromagnetic counterparts. And WST fits perfectly well in this framework with the high sensitivity that it can reach, its large field of view where fibers can be positioned, and also the panoramic field of view of the EFS, and its unprecedented level of multiplexing. So within the WST Time Domain Working Group and the Division 4, that is the Multi-Messenger Observations Division of the ET Observational Science Board, we are studying possible observing strategies to adopt with WST to research electromagnetic counterparts of BNS detected by next generation interferometers. We are considering two main possibilities, either to use WST alone performing a galaxy targeted research, and in this case it's important to have an idea of the number of galaxies that need to be targeted, and I'll come back on this later, or also it can be used in synergy with the optical near-infrared photometric observations targeting the counterpart candidates provided by other facilities. But let's start by seeing what are the properties of the counterpart that are detectable with WST. To understand this, I did simulations with the exposure time calculator of WST, starting from simulated datasets of ET-BNS and the corresponding electromagnetic counterparts provided by the Gran Sasso Science Institute group, to see the detectability and characterization of these counterparts with WST, and to see if the results depend or not on the observable and intrinsic properties of the BNS population. Observable like redshift, degree and angle distributions, and intrinsic properties like neutron stars equation of state and mass distribution. A bit more in detail, I took into account for different configuration of ET with the delta configuration and the 12 configuration with a cut on scale localization at 100 degrees squared. And also I took into account for the configuration with Cosmic Explorer in the network with a cut on scale localization at 40 degrees squared. Then the counterparts were kilonovae populations calibrated on ET 2017 GFO, or more generic theoretical models, and also we took into account for the contribution of the afterglows. Then I computed signal-to-noise ratios in EFS and MOS blue, orange, and red arms for 30 minutes and 60 minutes exposures. Now, going to preliminary results, you have here the detectability, that is the percentage of detectable kilonovae as a function of time post-merger, different colors corresponding to different signal-to-noise ratios and different lines corresponding to different arms of the spectrographs, results for DFS on the top and for fibers on the bottom, and for a model, a GFO-like kilonova model on the left, and for more generic theoretical models on the right. In any case, you can see that the best time to trigger observations is about 12 to 24 hours post-merger. Now, from the left to the right, you have the redshift and magnitude distribution of WST detections and the contribution of the afterglow to WST detections. In these two plots, The white background histograms refer to the kilonova parent population. Gray distributions refer to the kilonovae that are detectable with the Vera Rubin Observatory, while colored ones refer to WST detections. Different colors always correspond to different signal-to-noise ratios. In particular, in this plot, there is this black line that refers to the right-hand side y-axis and gives for each redshift bin the fraction of kilonovae that are detectable with WST with respect to those that are detectable with Rubin. And you can see that up to redshift 0.2, almost all kilonovae detectable with Rubin are also detectable with WST. And in general, we can access with WST redshift of 0.4 and magnitude about 25. In this plot instead, you have the viewing angle distribution of WST detections in those cases where the kilonova is outshined by the afterglow. And you see that it happens mainly for on-axis and slightly off-axis systems at all the times post-merge that we are sampling. Concerning sky localization, that you have here as a function of redshift for BNS detected by ET alone and ET in a network with Cosmic Explorer, you see that having another interferometer in the network improves a lot the precision on sky localization. For reference, you have here as a black dashed line the WST field of view. And sky localization is very important to perform the follow-up and to point the telescopes. So we can imagine to do this follow-up, for instance, with WST alone. We can imagine that we receive a gravitational wave alert with information on sky localization. So we have a two-dimensional error region. And on the luminosity distance with the corresponding error on the distance estimate. So we end up with a three-dimensional error volume in which we will have a huge number of galaxies to target. To have an idea of this number, I computed the comoving error volume for each BNS and then the number density of galaxies from galaxies luminosity function of different redshift to obtain finally the number of galaxies that are consistent with the gravitational wave three-dimensional error region. I obtained something like this. On the left, you have the number of galaxies in the error volume of each BNS. Every point in this plot is one BNS as a function of redshift. Different colors have just different magnitude intervals, and this black line refers to the number of WST fibers for comparison. And to be clearer, on the right, you have the probability distribution function for the overall population. So for galaxies here with apparent magnitude lower than 25. To have an idea of what WST can cover in one night of observations, we did this exercise plotting the number of galaxies in the error volume of each BNS as a function of sky localization. Then within one exposure, we will be able to cover in principle one field of view of WST and have in principle 30,000 fibers available to target galaxies. Then if we are doing 1 hour exposures and we assume that one night of observation is about 8 hours, what WST can cover is this. This is the fraction of events for which the number of galaxies in the error volume is accessible with WST alone. That is pretty good for the events localized better than 25 degrees squared, if we consider also that these white points are really at the redshift horizon that we consider. Here I'm considering all BNS with a redshift lower than 0.45, and these are events at that redshift. Now, if there is only the Einstein Telescope in the network, this changes completely. This becomes the number of galaxies as a function of redshift, and this is because the errors on sky localization and on the estimate of luminosity distance are bigger, and of course also the fraction of events that can be covered with WST alone is lower. We identified a sample of golden cases, so a sample of events that are well suited to be followed up with WST alone, that are for ET in a network with Cosmic Explorer, those events at redshift lower than 0.3 and with sky localization that are lower than 10 degrees squared, for which the number of galaxies in the error volume can be covered with WST with a limited time of exposures, with a limited number of exposures. In this case, for instance, 3 exposures would be sufficient. Those events are more than 5,000 over the whole sky, so we should take into account for a cut of the events that are seen from WST location, and also over 10 years of observations with gravitational wave interferometers. If we consider ET alone, the golden events are in this case at redshift lower than 0.2 and with scale localization lower than 10 degrees squared. And of course, these are less events, about 100 events over the whole sky and 10 years of observations. Now, of course, it is even better if we consider those at a scale localization below 1 degree squared that are more than 400 for ET in a network with Cosmic Explorer. Of course, this is in terms of a comparison of the number of fibers with the number of galaxies, assuming like 1 fiber is 1 galaxy, but there can be possible issues with this strategy. For instance, the kilonova and the host galaxy can be superposed and the host galaxy can outshine the kilonova. Or also the kilonova, the electromagnetic counterpart, can have an offset with respect to the host center and we risk to miss the detection. So we had a look at the magnitude of galaxies at redshift lower than 0.5, also limiting ourselves to shorter host galaxies. And we saw that typically galaxies are brighter than kilonovae, and in these cases we would need the spectral subtraction to have a detection. On the other hand, we looked at the offsets of short GRBs with respect to their host, and we saw that these offsets are typically larger than the fiber's aperture and than the host galaxy effective radius. Also, when looking at the magnitude, at the surface brightness at the short GRB location, we saw that this is typically comparable or much fainter than kilonova magnitude. So in this case, the detection would be easier, but fiber bundles would be needed to avoid missing the detection. And of course, with DFS, we would not have this problem. Now, as I mentioned before, we have also an alternative strategy that is to target the counterpart candidates provided by other facilities like the Vera Rubin Observatory. So that will scan probably with target of opportunity observations the error regions, providing a lot of detections that are not associated with any transient classification, and spectroscopy allows us to do this, to classify them and to find the electromagnetic counterpart. So with this, I'm at my conclusions, and yes, so integral field and multi-object spectroscopy with WST are really well suited for the identification and characterization of electromagnetic counterparts of next generation gravitational wave detections. The possible strategies are either to use it in a standalone scenario or in synergy with the optical and infrared photometric observations, reaching redshift limits of about 0.4 and magnitude 25 for kilonovae, while the afterglow contribution is observable for on-axis and slightly off-axis systems, and of course also at high redshift. Thank you very much for your attention, and I'm happy to take questions and to discuss about this.
Thank you, Sofia, for this very fascinating talk. We now open the floor for questions and discussion. If you have questions, please raise your hand or feel free to text the questions in chat and I will read it out loud. Other questions? If not, for example, I want to know your idea about the tension, the Hubble constant tension and the gravitational wave events. What do you think that will be the future for this kind of topic?
I think that, well, it's not my specific domain. I just think that with the next generation gravitational wave interferometers, if we have the detection of the electromagnetic counterpart as much as possible, then we will have the good statistics to solve it.
Thank you. questions for Sofia? No questions. You are safe. That we can close the session here. Thank you again, Sofia, for your talk and for sharing your work with us.
Thank you.
All for joining this session, and we will see again for the next talk that will be Dr. Eloisa Poggio on July 10. Have a great day, everyone, and goodbye. Thank you again, Sofia. Bye.
Bye. Thanks a lot.